I hope this is a very friendly discussion today on wireless power transfer. And to start the discussion today, the first question I have here is if you can present yourself, who you are, what you do, and why you are interested on this topic of WPT.
Oh, no, that's a great question. To start with, my name is Greg Durgin. I am a professor in electrical and computer engineering at Georgia Tech in Atlanta, Georgia, in the United States. And I've been here for 22 years. And while it wasn't my intention when I first started here, I was coming from kind of a wireless comms, cellular communication background. I quickly got into wireless power through RFID and the low power stuff. Um, which really I found it was a great way to get students excited about research because they like this kind of almost sci-fi application of powering up electronics from a distance and making it do work for you. So we started a research group here largely around RFID at that time. This would have been about 2003. And then our work kind of got some attention from the higher power circles of wireless power transfer. And I was approached by Daryl Preble of the Space Solar Power Institute, which conveniently is here in Atlanta. And we started to do some high power work as well. He helped uh, with a big SATCOM project that we did back in 2011, which was the first real foray into the technology that we did. And we've been studying it ever since because it's a really rich field and I think strategically important for all of humanity, really.
And why do you start also thinking about the solar-based solar power if you can give some words about what it is and why you think this is a viable and real
That's right. That's right.
solution.
So the space solar power is a very old idea. Like there was a patent, I think it was 1971 by an engineer named Peter Glaser who said, well, you know, listen, we have this energy crisis on Earth. We need more megawatts. The problem is, and what really the opportunity is, there's a tremendous amount of power already in space. I think I did the calculation once. In 10 minutes, there's enough sunlight that hits the Earth to power all of electricity for a year for all of mankind. So the problem isn't that there's not energy, it's that you have trouble bringing it down to Earth in a usable form. And so Glazer's idea was, okay, you just put solar panels in space, gather it in space where the sun doesn't set, beam it down on what is most likely a microwave link to the surface of the Earth, collect it where we can collect very microwave energy very efficiently, then tie it into the grid and supplement all of these other non-renewable forms of energy that we use, like coal, gas, and some of the other more problematic ones like nuclear, et cetera.
Yeah, but do you think this is feasible or it's still a science fiction
Oh, yeah, yeah.
project?
So I think in Glazer's day, it was very much science fiction. It was probably like 3 or 4 orders of magnitude away from profitability. This is if you look at 1960s and 70s technology, everything was big and bulky, right? All the electronics were big and bulky, let alone the spacecraft that you send up. Over the years, we've made a lot of progress towards making things more efficiently. We've gotten a handle on the microwave power transfer. I'm personally very positive, more positive than I've ever been on space solar power technology because I feel that we now have a technology pathway to get to a profitable system. And that's one of the things I've always emphasized is what we really need to do is look at the profitability. How much energy can I get versus what is the cost to build it out and launch? And I'll probably put some numbers to those as we talk about it. Um, but yeah, I think that we're getting very close, especially with some of the privatization of launches, the launch costs. have gone down considerably. And once they get somewhere in the range of 200 to 300 dollars per kilogram to LEO, low Earth orbit, I think you're going to see some really surprising things uh, in the space solar power world. Um,
So what you are saying is that the limitation is really the access to space. So from the other point of view, everything is resolved, and this is the main issue, or do you think there are still?
that is a great question. And so I want to break it down into some economics. Let's talk about the ground first. And one of the reasons why space solar power is so compelling. The natural instinct is, hey, why don't you just put solar panels on the ground, right? Like just there's already sunlight hitting the ground. Why have a big collection station for microwave power transfer that's really big and bulky and expensive? And the key to that is to realize that if you put solar cells on the ground, you can convert, 30 couple percent in the best case scenario efficiently of what's impinging upon the Earth. So at high noon, if you're at the equator, that's going to be about 300 watts per meter squared. Now, keep in mind, that's when the sun is directly overhead. It's only going to spend a couple hours directly overhead. You start to get foreshortening losses on either side of that. And of course, over half the time, you don't even get sunlight because of nighttime, or you have weather effects or things like that. So what's interesting is that for most space solar power designs, you get about the same converted watts into energy per square meter of terrestrial infrastructure as you do at the peak of a terrestrial solar power grid. You bet about 250 to 300 watts per meter squared. But of course, the space solar power one, if you're using a geostationary Earth orbit satellite, that stays constant throughout the day and the night. There's only a little bit of time during certain seasons when you enter into eclipse and you won't be able to transmit. But this isn't midnight when it's not, electricity isn't in particular demand. So the long and the short of it is you wind up getting about 10 times more megawatts per unit area of a collection farm on the Earth. And that's a huge savings. It's a huge savings in land and the opportunity cost for using land, the infrastructure for building it. And another consideration is that a space solar power rectinifarm that collects microwave energy is much cheaper to build out than a terrestrial solar farm. The reason being is that you almost the receiving devices almost look like giant RFID tags. They can be made as like peel and stick appliques to a piece of glass that's tempered and weatherproofed. And what's more, you can make things transparent. So the land is still getting some sunlight. You can graze animals underneath it, do agriculture. And so there's kind of this dual use capability that you don't get with terrestrial solar. So charitably, you get about 10 times as much energy per units kilometer on the ground with space solar power. But of course, the big thing is the launch costs and the amount of infrastructure that you have to put into space. As a general rule of thumb, for every square kilometer of collection site you have on the ground, you're going to need a square kilometer into space. So that's the bad news. That's very intimidating. But the good news is that it doesn't take a lot of mass to make a space solar power satellite. It takes a lot of area. And I think that's one thing that if people sat back and did some number crunching, they'd realize that this isn't nearly as intimidating as it looks. In fact, just the build out, not launch costs, but just the build out of the infrastructure in space, when we look at mass produced quantities, it will be less than the Earth build out on the surface of the Earth because you don't need a lot of mass. You don't have to content with conventional weather. You have space weather, which is a completely different thing altogether. That's something that you don't necessarily need mass to contend with. There's a lot of other issues as well, but you can get away with relatively lightweight structures in space. And so really it comes down to launch costs, right? How do you get the thing to be profitable from a launch perspective? The all the privatization of space and Elon Musk, they're only going to get you so far. What you have to do is make a lightweight spacecraft. And so we have this benchmark of very low area density for our spacecraft. We want spacecraft that whose kilogram per meter squared is very low. Kilograms will tell you how much it costs to launch. Meter squares is going to basically tell you how much power you collect. And what's interesting is that if you do the economic analysis, you say this is going to launch a satellite. It's going to last 15 to 20 years in space. We're going to beam it down on a microwave link. What you find is that you could probably get, under today's launch costs, a break-even type of space solar power satellite just shy of 1 kilogram per meter squared. Now, we've never built a satellite that's that thin before, but the physics are actually sound. In fact, just to give a little reference, I always do this in my talks because everybody understands smartphones. So I bring out my smartphone. It's just a standard, I don't know, 4 or 5 year old smartphone. And if you tiled these together and you made like a square meter, I think it'd be about 15 kilograms. So much thicker than what we're talking about. But of course, this smartphone has a lot of extra things you don't need for a spacecraft. It's got a screen, it's got huge batteries, it's got a titanium case for all the terrible things that I do to my phone on planet Earth with gravity. If you were to break this apart and pull some of the circuit boards out, those circuit boards are less than a kilogram per meter squared. So we're not talking anything that's science fiction. We're just talking about something that's very different from the way that we normally design a spacecraft.
Yeah, but if you, even if I launch something like this, if I have the capability, the numbers I heard is thousands of square meters or hundreds of square
That's
meters,
right.
antennas. And how can I build such a structure in space? I don't have, because you're saying that it's more expensive to build it on Earth than on space, but on Earth I can have technicians, I can
That's
have people
right.
that go there and build a thing. In space, unless I have a group of astronauts going there and try to put all the things together, how can we build it?
So that's a great question. And there's probably not one answer to that. We have different people in the space solar power community that has different ideas about that. There are some ways to kind of robotically or autonomously interconnect some infrastructure. So you launch a lot of little satellites, and it's almost like your favorite Saturday morning cartoon. They become the big satellite, and um, I think that's certainly doable. We have some pretty neat designs on there that can work that way. I also know that there are some researchers that have some fleet formation designs in which you have a bunch of small identical satellites then cooperate like a larger satellite. But that is definitely an engineering challenge. And I don't think we have like one answer in the community at that. We just have a couple different avenues that we could explore for that.
Yeah. No, well, if you want to share some slides, feel free, but we can continue chatting because, to be honest, my okay, even if I am able to build this huge structure in space, then I
Right.
have to beam the energy down.
That's right.
And as you were saying before, you came from a telecommunication area. Me too. So we are used to use traditional antennas for telecommunications. And these antennas for telecommunications, they normally work in the far field zone. But when you work on the far field zone, you lose a lot of power. because you are in the fast field zone. You are actually your electromagnetic beam is already diverged, and you have power all over the place. To say it easily, my question is, what do you have to do on the antenna side so that we can actually guarantee that most of the energy will be collected on ground? And this is something that I still don't see a lot of people talking about it.
Yeah, it's honestly it's the hardest part of the problem. Um, and so there's some reticence, I think, sometimes to deal with it, but there are some pretty neat ideas out there and some people working on this problem. I'll go ahead and share my screen. And so this is my standard introducing a student to uh, Fresnel zone, Fresnel field wireless power transfer. Here's the surface of the Earth. We'll call it our target surface.
Mhm,
There's a spot on the Earth where you have a green collection area. That's your rectiniform receiving the wireless power from space. There's your transmission aperture that you somehow built in space. Just be agnostic about how it got there at the moment, for the moment. Then you have some sort of separation distance. Now, the trick to these technologies is that every single element or region, I should say, on this transmission aperture has to be able to focus so that at the center of this target, everything is the same phase so that you add
mhm,
constructively in your waves. So it's really no different than any other array. It's just that whereas if you want a maximum far field uh, pattern, you basically have to make everything transmit the same phase across that transmit aperture so that when you get really, really far away from it, you get a peak that's in phase. Here, you get maximum focusing. If you don't do that, if you actually taper the phase and basically make this point on the end have a phase offset that compensates and gets back to the same phase as a transmission from the center or a transmission from the other extremity. Now, when you do it that way, what happens is as I move along this target aperture, at some point, I'm going to get more path difference from the end than I do from this edge, and I'm going to start to destructively interfere. And that's going to very rapidly wipe out my transmit power. So I get sort of a bubble spot right there. Uh, and it turns out that this really simple formula tells you about when you're going to get more than 50% of the power. It's called the diffraction limit, diameter of the transmit aperture times the diameter of the receive aperture has to be at least the separation distance times the wavelength that you're using. So that's the basics of how this is working and how you phase things. Of course, the biggest part of the challenge is that we need to be able to measure this phase offset on the extremities and everywhere in between to adjust to get the focusing right here.
mhm.
And if you think about it, like that cannot be mechanically stabilized. That's the mindset that most of us SATCOM engineers
Yes.
approach this problem with, like, oh, I'm going to have a dish and it's going to have, perfect, no aberrations. And the problem is when you get to a kilometer plus infrastructure in space, even if you could somehow make it perfect, you are still going to have things like minor gravitational pulls from the planets or the moon or the sun or the mascons on the Earth. These are the irregular densities that tug and pull on a spacecraft in orbit. You're going to have some heat gradients that cause a little bit of flexure. Most of us like to transmit this somewhere around the C band for space solar power. That's where the wavelength is about 2 inches or 5 centimeters.
Mhm.
And of course, uh, that's a tiny amount of it. If you get more than a centimeter out of whack on your positioning on one end of the spacecraft, that's going to start to destructively interfere, and you're going to mess up your combination with the other part. And so there's a need to design pilot beams and some form of what we like to call retrodirectivity that basically reverse the pilot beam and send it back down. We had a great speaker this time around, Neil Buchanan, from the UK who was doing a really neat project on retrodirectivity for space solar power. He was working on a helical array, and he's actually transmitting a beam, reversing it in real time with a spinning type of helical structure, which kind of mimics Cassiopeia, which is a type of
Cassiopeia, yeah, yeah.
yeah. So he shows the hardware. Now, it's a lot of hardware. It's very difficult to reproduce at very thin electronics, but not impossible. And
Mhm.
he's shown that you can employ this retrodirectivity so that you send up a pilot beam and it all focuses back down to the right point.
So, and looking to your formula here, it is related to lambda. So, this means that the frequency of operation will have an impact on this, right? So, what do you think is the, I will not say the best, but the optimum frequency
You
of
can go ahead and
operation
say
for
the
this?
best, and I'll give you an opinion that offends a lot of people, and that's fine. They're not here to defend themselves. So the general consensus in the field is you cannot possibly go over 10 gigahertz. Wavelength is higher frequency means smaller wavelength.
Yeah.
And smaller wavelength is good in this equation because it means that you can do an exchange between a smaller combination of transmit and receive sides. Um, and everybody wants to kind of minimize. I don't think that's necessary. If you can do it for a half a kilometer, you can do it for a kilometer. And what's more, you're going to have at least as much infrastructure for grabbing solar power in space as you will for beaming down on a microwave link. So, I mean, in the grand scheme of things, I'm not too worried about going higher. But what you do worry about when you get too high is things like water absorption, cloud absorption, some of the molecular resonances in our atmosphere by oxygen and nitrogen. And then the weather dependence, like raindrops, will actually start to scatter above 10 gigahertz. The wavelength will get so small that it'll become the size of a raindrop, approach the size of a raindrop, and start scattering out. So if you want that really valuable constant baseload power washing over your Rectenna farm at all times, we think under 10 gigahertz. I'm personally a fan of the C band, 5.8 gigahertz. I know if you had asked the Caltech people, they've chosen 10 gigahertz. They're kind of pushing the envelope on the
Yeah.
atmospherics, which is fine. And I know a lot of the reference studies and some people like Cassiopeia, I think they do 2.4 gigahertz, like your microwave oven. So somewhere that roughly bounds the space in terms of frequency for the technology.
Yeah, I know also that the ITU is looking to the 5.8 gigahertz as a possibility, mainly because the colleagues from Japan are pushing that frequency, which probably goes into favor what you are saying. So, and what is your vision also between geostationary, where in principle your transmitter is, I will not say fixed, but it's very stable,
Yeah.
versus having a Leo constellation to do something like this? What is your vision on that? Have you thought about that?
Absolutely. In fact, you've definitely done your homework because this is another one of those very contentious. There's the unified front that we all like to put on as space solar power people, and then when we get like ourselves locked in a room, we have fights over Leo or Mio or the Geo. So I am a big fan of Geo, or maybe more specifically, I like to think of it as a quasi-stationary, quasi-geostationary Earth orbit, a QGEO. So a geostationary Earth orbit, of course, for those that don't live and breathe astrodynamics, it's you go about 36,000 kilometers away from the surface of the Earth. If you're in a stable orbit, that magically matches you to the rotational period of the Earth. Your satellite will hang in the sky at the same point in latitude, beaming down to the surface of the Earth. And that's actually really good for infrastructure because if you don't put it there, then if the US launches a satellite and they want to talk to a US ground station, well, over time that will slowly go over to Europe and China and Russia and Africa and all these other places. So unless you've got some sort of agreement for sharing satellites, uh, then then it becomes kind of an expensive duty cycle issue. Like anywhere other than geo, you're going to put this satellite up there, and it's basically, you're only using it part of the time. which all of a sudden takes a huge penalty in the economics. We got to make this thing work economically.
Hmm.
So there are some other solutions. Caltech is doing a MEO design, medium Earth orbit, which means it's going to go around the Earth from your vantage point of a fixed location on the Earth. They actually have some really clever designs for basically how to synchronize the orbit with like the demand usage of regular utility grid electricity. Um, there's some people that like LEO. They love that really low transmission distance, that small R that's on the
Hmm.
slide here.
Yeah.
They love that. I don't like LEO. Not only do you have a duty cycle issue, but you also have a debris issue for the types of, but by definition, we're talking about a really big satellite with a huge cross-sectional area.
Hmm.
The probability that a satellite like that will experience a catastrophic collision in LEO, where we have so much junk already during the course of a 20-year lifetime, is pretty close to one, from what I can tell, because they're just so big. It's so much area. It's a huge target. And so I'd be very concerned about launching one of these into LEO. But to
Yeah.
get back to GEO, that's a very valuable real estate in the satellite world.
Yeah.
And the one nice thing about space solar power that we have going for us over a conventional communication satellite is that, your conventional communication satellite, it wants to be at the same point in the sky at all times. So you can hammer down and put your dish antenna and sight it in perfectly and get good spatial rejection of any interference, any co-channel
Hmm.
interference. You don't want the thing wiggling around.
Hmm.
Space solar power is different. You can tolerate a lot of wiggle as long as you're above the location in the sky. So if you add some eccentricity and some inclination, you can still have a geosynchronous Earth orbit, but it's not necessarily geostationary. From your vantage point on Earth, it might warble around in the sky.
Hmm.
And you can design the orbit in a way that steers clear of geo completely, a couple hundred kilometers at least, and it still illuminates that same spot on the ground. The rectenna doesn't care about signal to interference ratio. It just wants to gather the power. So you have a degree of freedom there that the comms engineers don't have when you're designing the RF link.
Yeah. What I see on the Geo versus Leo is on the Geo part, you your receiver is fixed, and you will decide where you are going to put your antennas, and there will be a fixed area. But if you look to Leo, you can do what they are calling power on demand. So I can call and say, bring me a 10 watts to my house. With Geo, it's very difficult to do it, right? So um, yeah, but I agree with you that Leo will create a lot of debris, and yeah, that's
Yeah,
that's
well,
that's another.
you could probably do some clever things with Leo to protect against the debris problem. Like
Mhm.
some of our paddle sat stuff, I think would work well in Leo actually, because it kind of self clears. It has this ability to self clear when you damage it or if the lifetime finishes up. But yeah, at the end of the day, if you want to make a dent in the electricity usage of mankind with space solar power,
Yeah.
like people worry about the R from a microwave point of view, but really, yeah, you might shrink the apertures and stuff, but you still need so many acreage, so many square kilometers of
Mhm.
solar cells in space. And that's not really going to change no matter where you put the satellite.
Yes. Yeah, for sure. And also looking to these structures, um, what do you think about the technology to be used in space and ground? Silicon is probably not the best option. Gallium arsenide does not have the power, let's say, need. So gallium nitride is a possibility, or you are foreseeing other technologies to use in this approach?
Yeah, I think gallium nitride is a really good technology at the transmitter side because, of course, that does a lot of power and it does it very efficiently. That might be the way to go for that. For the ground station side, I actually like silicon because I think you can probably make it at these frequencies relatively low loss. In fact, one of the things that we were discussing at the Space Solar Power workshop, which meets annually at the Wireless in Space and Extreme Environments Conference, IEEE conference, it was in Halifax just a couple weeks ago. We were discussing that really just a passive rectifier is not the way to go. What you need is something that, like what we use on RFID tags, except for there it's usually geared for low power. We would want to gear it for higher power, but it would basically have a dynamic matching front end and then a charge pump that would dynamically load the rectenna. And frankly, if you made it out of silicon, there are some designs you could probably get that pretty close to 90% efficient or 85% efficient.
Mhm.
But yeah, if you
Mhm.
had the luxury of doing things in gallium arsenide, that might be even better. But sometimes in mass production, you got to go with what's cheap.
Yes, of course, of course. And looking now to the Hecten apart, so from a geopolitical challenge, how do you see two things? One, the impact on humans and on animals about such um, a link, and
Yeah.
versus also the geopolitical issue of I'm collecting energy up in the sky and send it ground to ground. How do you see this more, let's say, social impact of these technologies?
Yeah, that's great. Okay, we got to take these one at a time. The geopolitical one is a big one. I honestly think that's the scariest aspect of space solar power. Um, and not that people are beaming power down to ground. I mean, any self-respecting microwave and engineer would tell you you really can't make a death ray out of these things. Like the coherence is just too hard. Now, if it was an optical system, like some people are,
Yep.
that's a different ball of wax. And that's one of the reasons why I like the idea of microwave power transfer. Um, but I think there's another issue geopolitically, and it's security. So, um, we just talked about how you have to have these pilot signals and a very carefully trained beam to get it down to focus onto the ground. By nature, that system has some susceptibility to jamming. Like if you get something at the site of the rectenna that jams upward, or perhaps you're able to insert temporarily a spacecraft in between the link, you could potentially degrade the link or knock it out completely if you're not careful about how secure you design the pilot beam. That's a huge issue. You know, the whole point is to make the grid as reliant as possible on space solar power because it's ultimately, I think it's going to be cheaper. It's also renewable, you know, no carbon emissions, at least if you don't count the launches. Um, and so if you look at the current, these are just US numbers, which are the ones I'm familiar with. It looks intimidating. You need a 1.4 kilometer collection site and a 1.4 kilometer transmission site in space. And if you want to replace the US electrical generating capacity 100% with space solar power, you would need 1,000 of those pairs. Now, that sounds really intimidating, but if you wanted to replace the US, we would need 10 times that if you wanted to do it with terrestrial solar. And in fact, the use of megawatts per kilometer squared of electricity generation, the space solar power on Earth uses less area per megawatt hour of generation than any other power supply, even nuclear, which is usually considered the best. And the reason is, yeah, the reactor is really energy dense, but you need a lot of infrastructure around it, usually a security perimeter here in the US. So that in terms of the megawatt hours per kilometer, it actually winds up being less than space solar power. But still, there's this mentality. I, I always call it kind of if you want to start a war, you use protons and neutrons. But if you're only using electrons, like nobody gets upset about that. You know, You can blow up a pipeline and it causes $10 million of damage and interruption in the supply, and everybody gets up in arms. But if you steal $7 billion of cryptocurrency, it's like, well, that was just electrons. So that's no big deal.
Nobody cares.
So then,
Exactly.
if you're not careful and you make satellites that uh, can be jammed with RF by an adversary,
Mhm.
in something that doesn't even seem like everybody to be an act of war, I think that's the biggest geopolitical risk.
Yeah. And I like that you said about nuclear. You think nuclear is better or worse than this technology? What I want to say is, from my point of view, probably nuclear is the solution that gives you more watts per whatever
Yeah,
for the
yeah,
cost. So what? How do you compare nuclear with this
yeah.
technology?
That's really difficult, right? Because you have to get into all these, land usage, it's close to a wash. I think space solar power
Hmm.
is actually better in terms of land usage. In terms of pollution, you actually do need to send methane or kerosene rockets up into space to launch the infrastructure. But I think in mass production limits, you're talking about well over an order of magnitude more energy down than that actually expends, which means we're doing much better in terms of the national natural gas and coal fire plants and gas
Hmm.
power plants that we use in the U.S. Um, in terms of the quality of power. And I think this is something that people are kind of waking up to. Like nuclear and space solar power actually provide the same quality of power, what we call baseload power, uninterrupted 24 hours a day. Not all energy that you dump on the grid is worth the same, right? The wind, as much as we love it, it's there when we don't need it. Um, and it disappears when we do sometimes. And that makes everything else work less efficiently on the grid. Um, right now, I think the US generates about 20% of its electricity with nuclear. And
Hmm.
that's non-negotiable. I don't think we can go below that level
Yes.
because the quality of the power is so good from a nuclear plant. You shut it down for like a week for maintenance, and that's it. And the rest of the time, it's this constant baseload power.
Yeah.
But that's kind of the power that space solar power also provides, is predictable, always there.
Yeah.
So, yeah.
Yeah.
So
Yeah.
they wind up
I
being,
understand.
I guess there's this X factor of, okay, every 20 years we have a nuclear catastrophe. There's trillions of dollars to clean up. And
Yeah.
I
Yeah.
think
Yeah.
I think the plants are getting safer. And I really do
Hmm.
believe that,
Hmm.
that I like nuclear power,
Hmm.
but there's that X factor that you don't have
Yeah.
that kind of catastrophic failure with space solar
Yeah.
power.
Yeah. And from a let's say safer point of view, solar based is probably much better than nuclear. So when we were discussing about this talk, you also talk about the RFT SAT project that you were involved, and you say it was the first space demonstration of microwave power transmission. Can you talk a little bit about it?
Oh, sure, sure. Let me
What
go
you
ahead and
did
show you a
on that
screen.
project?
This is one of those projects that your students and your colleagues do that probably doesn't get enough uh, talk time. Here's a summary of some space solar power
Hmm.
demonstrations. Here in the center, you have RFT sat. Here's a really neat 2020 Naval Research US test
Hmm.
module that was tested actually in space. Here's a really neat Kyoto. It was suborbital, but it was a rocket that did some power beaming. That's from the Kyoto guys, um, uh, Naoki Shinohara and Matsumoto.
Hmm.
And then they got the Caltech folks that recently in 2022 launched their Maple, which was a 10 gigahertz beaming experiment in space. But we had this three CubeSat back in 2019 that we designed with a custom radio at Georgia Tech. But the project was actually led by Northwest Nazarene University, two professors, Josh Griffin and Stephen Park. And their students, they're an undergraduate engineering institution. They actually integrated this whole thing.
Hmm.
And then
Hmm.
we built the radio at Georgia Tech. And what this thing was a 5.8 gigahertz source that there was a little boom that you put a rectiniform on and it kind of spindles out into space. And you could put some sensors and some computation on there. And then you'd had a little rectenna element that you powered up. And then it did some sensing and backscatter, and the communication link was all backscatter back to the main body of the satellite. And the goal was to demonstrate wireless power transfer and the ability to sense away from the spacecraft. There's some things that are easier to sense when you're not blocked by the body of the spacecraft, like radiation, magnetic field, et cetera. And this actually flew. We launched this in 2019. We energized it in situ in space. It worked. It took some temperature data back from the sensor,
Mhm.
and we published it, strangely enough, in the journal on RFID, because this is really just
Mhm.
like a big RFID reader in
Yeah,
space
yeah, yeah,
at
yeah,
5.8
yeah.
gigahertz. So I always tout it as like the first true space solar power satellite, even though it was this largely undergraduate research project. In fact, one of the
Mhm.
stories I like to tell from this is that it was a CubeSat mission from NASA. Those aren't funded with like enormous pocketbooks or anything. We were very limited in what we could do. Of course, it went over budget. Of course, it took way more time to integrate to get it off the onto the launch pad and into space. And so we cobbled together all sorts of volunteer efforts and teaching assistants at Georgia Tech to build the radio system and everything. And on their end, I remember at one point they ran out of money and they still needed some parts. So they decided to have a bake sale for their spacecraft. They baked cookies and brownies
Mhm.
and they sold them they're from Nampa, Idaho. They're out near Boise. And so that's how they raised the money for the last few components of their spacecraft. And then they were finally able to launch it into space and become part of the history books.
Oh, nice. So this satellite is a 3U, something like that. It seems like that, right?
Yeah, it's a 3 cube satellite.
Yeah, yeah. And the wireless power is that arm that is so the rectangle is on the top of the arm and the
That's
transmitter
right.
is
This
inside. Yeah.
this
Okay, I see.
arm
Yeah.
here that's on the dielectric boom
Mm-hmm.
that spools out kind of like a tape measure.
Yes, 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 yes.
And then the
What was
transmit
the
antenna
distance?
is up here.
Oh, I see.
That would.
What is the distance? Do you remember?
So yeah, so in on the ground, the distance could be 1 to 2 meters, and it worked
Mm-hmm.
perfectly. Now, nothing ever goes right in a CubeSat
Mm-hmm.
project, right? So when it launched, the boom failed, and it could only go out like several centimeters, but we still were able to turn it
Yeah,
on,
yeah.
reflect
That's
back, and get the data that we wanted to. So
good, good, good.
it's about,
So
I told the undergrads, that's about 80% better than most CubeSat missions, which wind up being space junk when they get up
exactly,
there.
exactly. So you in this graph you also showed the Caltech approach, which was similar to what you're showing, right? So they were beaming wireless power in let's say 1 or 2 meters in space, as far as understood, right?
That's correct. They recognized rightly that they actually had several experiments on this
Mm-hmm.
spacecraft that they flew in 2022. There was a 10 gigahertz array for beaming. They had a Rectenna module for testing and collecting that. They also had this really cool, like unfolding structure for the spacecraft.
Mm-hmm.
Um, where you kind of think of it as like rolling up your aperture into a rocket fairing, and then it kind of unfurled itself into this lightweight spacecraft, which, to be honest, as much as I like wireless power transfer, I think it's the spacecraft subsystems and the navigation systems in particular that need innovation and shrinking down. Um, and they rightly recognize that. So, our take on that, our latest take that we've been publishing papers on for the last several years has been this concept of a paddle sat, which takes it to like the
Yep.
next extreme, where you're actually using the solar pressure available in space to do your navigation. I mean, get rid of your propellant tanks and thrusters and save even more mass and extend the lifetime of your spacecraft.
Yeah, but this paddle sat or it's similar to electromagnetic propulsion, or is a different story?
It's a little bit different. So can show um, over here, a paddle
Hmm.
set uses the idea is once you get down to about a kilogram per meter squared, which is what you need to do to get space solar power profitable. At first blush, you run into this problem. So the spacecraft is so light that now you have an extra perturbing force on the spacecraft that you can normally ignore under regular spacecraft design. So you know that geostationary Earth orbit spacecraft for communications, or even the low Earth orbit ones, they tend to be big, bulky boxes, and they tend to be
Hmm.
relatively heavy with high volumetric density. In fact, as a friend of mine at SpaceWorks pointed out, uh, volumetric density in a spacecraft is almost like a proxy for how well you've done at designing the spacecraft. If you have really low volumetric density, kilograms per meter cubed, you haven't done a very good job of building a spacecraft. You need to pack that thing with instrumentation and take advantage of all you've got on the launch. But we're talking about low area density for a space solar power spacecraft, low kilograms per meter squared, under 1 kilogram per meter squared, really under 10 kilogram per meter squared. The solar pressure, basically the momentum exchange that Einstein predicted that you get with photons as they either absorb or reflect off of a surface. At Earth orbit, that's a sizable amount of force. It's
Hmm.
not the most predominant one for a regular satellite, but for this satellite, it's the dominant perturbing force. And that at first blush looks like a really difficult thing to contend with because you're like, well, now I have to have extra propellant to do station keeping and all this other stuff. But this is one of those problems that I believe you solve by leaning into it. Uh, when if you make the thing light enough, you can actually use the solar pressure by angling your solar cells and doing some other tricks to actually do all of your station keeping and your attitude control and some of the other type of mechanical navigation aids that you need to impart to a satellite. So then you can get rid of the propellant, which is usually the bottleneck for the lifetime of a
Hmm.
spacecraft, gets rid of more cost, and what's more, I keep telling people this is not a new idea. NASA guys thought of this 20 years ago when they designed the Messenger mission. And I have a picture of that here on the screen. So on the left, there's a spacecraft. It was a robotic probe, an orbiter that went to Mercury. Now, I do a lot of astrodynamics, and this fact surprised even me. It takes more propellant and energy and delta V in rocket parlance to take a spacecraft from Earth and insert it into an orbit at Mercury than it does to take a spacecraft and send it to Neptune and insert it. Even though Mercury is much, 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 much closer. And it's just the way that the astrodynamics works out because you're dealing with such a drop in potential, gravitational potential. And then the insertion takes a lot of energy into a small body like that. So one of the reasons we haven't been to Mercury very often as a species in terms of our probes. But this one probe that NASA designed and launched in 2004, Messenger, they knew that they had to make this thing bare bones, super light, and that when it got to Mercury, it wouldn't have hardly any propellant left, but it still needed to do science. So they had this really clever way of taking the solar panel, and keep in mind you're in Mercury, so the solar pressure, the amount of momentum exchange with the sunlight is actually a lot higher than it is on Earth, almost an order of magnitude. And by deflecting their solar panels, they were able to make orbital adjustments, attitude adjustments, and save some of their propellant as they inserted and made approaches to Mercury. And then just as a point of comparison too, and this is going to launch. The last thing I saw, they actually moved the launch date up to December of this year. We'll see if that actually happens because, US government, whatever. But the point is that some of my colleagues here at the Aerospace Corporation have this concept called a disk sat. It's a 1 meter diameter satellite. It's only about 2.5 centimeters thick. And it sort of maximizes the aperture for communication and power collection, and it minimizes. So if you look at this, the dry weight of this spacecraft is just a few kilograms. As if you take out the batteries and the propellant. It's got Hall thrusters. So these are the electric thrusters that you mentioned earlier when a conventional spacecraft that are pretty common now. But these, you're actually talking about a spacecraft that's basically in paddle sat territory. This is exactly what we need. And I don't even think the end use was actually space solar power envisioned for this. It was just a really cool, lightweight, stackable in a rocket fairing. You see the graphic on the right that they published, um, where you could put a whole bunch of these and deploy hundreds or thousands in a single rocket fairing. So I think for that reason, it's an old idea, and we're actually getting really close to the point where we can use that idea in practice. So I always tell people, uh, space solar power, we're not launching it in 6 months, but it's going to hit a lot faster than people realize, and it's probably going to make catch a lot of bright people by surprise.
Oh, yeah, for sure. And it's amazing that it combines a lot of knowledge from electrical engineering, aerospace engineering, mechanics, and robotics, and so on and so on. This is what
Oh, it's
I think it's amazing. Yeah,
it's a playground for sure.
exactly. So I think I have one last question. And my last question is, if you are in front of a group of PhD students or master students that want to come to this area, what do you think, or what you'll say to them? What is the hot topics that they can do their research and take a PhD on this topic? What do you
Oh, yeah, yeah.
propose to them?
That's a great question. I always tell them that, first of all, just pick anything in space solar power and work on it, right? Whether it's pilot beam design, aperture coherence, making transparent rectiniforms that are super low cost, and yeah, just pick something. There's so many fun things to work on. And you know what? You're not going to get hired. If you finish up in the next 6 months, you're not going to get hired by the space solar power industry. But you'll have all this cool knowledge about RF electronics, arrays, and like, those people walk into huge high paying jobs nowadays, and we desperately need them anyway. So you don't have anything to lose. Uh, just try something hard in the field. Just pick any aspect of it, whatever interests you.
Yeah, amazing. Thank you. Can you stop sharing so that we
Sure.
see our faces? Yeah, good. And you talk also that you publish these results on the RFID journal, which I think is a very good journal. But there is a new journal coming up starting January on IEEE wireless power transfer journals,
We would
which
have
I think
published there
is
if it had existed.
exactly, that
That's a
is a
great
new
journal. It's going to be fantastic.
opportunity to publish your results. And again, Greg, thank you very much for this talk. I think it was amazing. I think there are a lot of ideas, and hopefully we can bring more community to this topic, more students, more companies, more engineers, more professors. And once again, thank you very much for spending 1 hour here talking about this amazing
It
topic.
was
Thank you.
it was my pleasure. Thank you for having me.